page 652, section 9.4. On page 652, they give me 5 formulas called the sums of powers of integers. There are 3 of those formulas that we use in calculus, and of course, since this is pre-calculus, then anything that we're going to utilize there that we come across here, we want to be sure that we look at. So of those 5 formulas, since we use the first 3 in AP Calculus, those are the only 3 that I'm interested in you knowing. So you need to know those 3 formulas for your quiz and for your test. Just those 3, not all 5 of them. So let's talk about what those 3 formulas do, all right? The first one is the summation of I. The second one is the summation of I squared. And the third one is the summation of I cubed. So the idea is, if they ask me to find the sum of the numbers from 1 to 50, I could use this first summation formula to help me do that, where I could say, okay, if I'm finding the sum from 1 to 50, then I'm going to go through and see that 50 would be in the place of n, so that would just be 50 times 50 plus 1 divided by 2. If instead they had said find the sum of the first 50 squares, that's like 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is, find those squares and then go back and add them, that's what this formula will find for me. So again, if n is 50, then that would just be 50 times 50 plus 1 times 2 times 50 plus 1 divided by 6. Or if we wanted the sum of the first 50 cubes, like 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is all the way on up to 50, then that's what this formula finds. So that would just be 50 squared times 50 plus 1 squared over 4. The power of those 3 formulas is that they enable me to solve a problem like we see down here. Now, there is nothing like this example in your textbook, but this is why we want to pick up these 3 summation formulas. This is how we would use them next year. And so this is going to be your bonus on next Friday's test. So you can decide whether you want to play around with this example before the test, or whether you just want to go, I have enough to deal with already, I'm not going to worry about that. You do have to know the 3 formulas for the quiz and for the test. Those aren't optional, but this process down here that is not in your textbook is optional because it's going to be the bonus. Okay, so let's look at how one of those works. If I had the summation from 1 to 50 of x squared plus 2x, at this point, the way that I would have to do that problem is I would have to say 1 squared plus 2 times 1, plus 2 squared plus 2 times 2, plus 3 squared plus 2 times 3, plus, and I would do that all the way to 50, right? Gonna take me forever. There is a much better way of doing that, and with these 3 properties, I can do it. So we already have been giving properties about summation, that if you have the summation of something that's being added or subtracted, that you can break that into separate summations. So that's what we've done here. We've broken this up into 2 separate summations, x squared and 2x. We also had a property that said if you had the summation of a constant times something, that you could pull that constant out in front and just do your summation, and then when you were finished with the summation, then you could multiply back through by the constant. So that's what we've done in this first step. We've broken this into 2 separate summations, and we've pulled that constant out in front. So now it's just an issue of using those formulas. So if they say, what's the summation from 1 to 50 of x squared, that's going to be my squares formula. So I'm just going to put 50 in the place of n. So that would be 50 times 50 plus 1 times 2 times 50 plus 1 divided by 6. Throw that into my calculator and I get 42,925. For the second piece of that, I have the summation from 1 to 50 of x. So that's my first formula up here, where again, I'm just going to put 50 in the place of x. So that would be 50 times 50 plus 1 divided by 2. And then remember we had that constant of 2 out in front, so we're going to multiply by that as well. So when I multiply, I'm going to get 2,550. Add those two together, and I have the summation that otherwise would have taken me easy the whole front of an 8.5 by 11, right? And somewhere in there I'm going to get one number wrong and it's going to mess the whole thing up. So much better way of doing this, and so we can see the power of those formulas in an example like that. So that is the only thing that we are going to do from section 9.4. Just those 3 formulas and a bonus application of them. All right, so let's look at section 9.5. Section 9.5 is the binomial theorem and Pascal's triangle. The binomial theorem and Pascal's triangle. All right, a binomial is just something that has 2 terms. Like x plus y right here is a binomial. We want to use Pascal's triangle and the binomial theorem to help us do binomial expansion. What do we mean by binomial expansion? Well, that's when I have something like we see here, x plus y to the third, and we literally go through and expand that x plus y times x plus y times x plus y. We literally multiply it out. Not really a whole lot of fun. I definitely could do it, but I'm going to need to FOIL here, x plus y times x plus y. When I FOIL it out, will give me this trinomial, and then I'm going to have to multiply this trinomial times this binomial. So I'm literally going to go through and take x times every one of these terms, and then I'm going to take y times every one of these terms, and then I'm going to have to combine like terms. Man, that's a lot of work just to multiply something to the 3rd power. Okay, well then what am I going to do if they want me to do it to the 5th power? You're kidding, right? Like you literally want me to take this and multiply that by x plus y again, and then multiply it by x plus y again? Like my answer is going to be humongous. Then if I hit something like x plus y to the 21st, forget it, just go ahead and count that one wrong. I'm just not even bothering with that one, right? There has got to be a better way to do this, and there is. That's what we're going to use Pascal's triangle and the binomial theorem to help us do. All right? So, several things about Pascal's triangle on page 656 that we want to notice. First off, they tell me that the nth row is going to go with x plus y to the n. The nth row is going to go with x plus y to the n. So when I'm looking at the 2nd row, that would be the expansion of x plus y to the 2nd. If I literally did x plus y times x plus y, I would get 1x squared plus 2xy plus 1y squared. That's where the rows of the triangle come from. The second thing is that when we count our rows, it starts with the 0 row because I need to start with x plus y to the 0. So I need to be sure when I'm counting down, I start counting with 0 and then 1 and then 2. I start counting with the 0 row in Pascal's triangle. The numbers in Pascal's triangle have a particular pattern to them. Notice that the first number, the coefficients, the first number in every row is 1, and the last number in every row is 1. To get the other numbers from the triangle, you literally add the 2 numbers above to get the number down below. Like this row started with 1 and ended with 1, and to get this 2, we added the 2 numbers that were up above it. 1 plus 1 gave us 2. This next row started with 1 and ended with 1. So to get the numbers in between, we added 1 and 2 and got 3. We added 2 and 1 and got 3. Started with 1, ended with 1. Add the numbers 1 and 3 gave me 4. 3 and 3 gave me 6. 3 and 1 gave me 4. So that's where we're getting the numbers or the coefficients in Pascal's triangle. So if I wanted to just go create the coefficients of Pascal's triangle, I'm going to start with the 0 row, which is 1. Then I'm going to have the first row. It's going to start with the 1 and end with the 1, so there won't be any room for any other number in between. Then on the second row, it starts with a 1 and ends with a 1, and I'll add the 2 numbers from the row above it to get the number that goes below. So you help me with the next couple of rows here. What would the next row start with? 1, and then 3, 3, and 1. Right. How about the next row? What would the next row be? 1, 4, 6, 4. Perfect. How about the next row? 1. Yes. 1, 5, 10, 10, 5, 1. And we could just keep going, right? As far as we needed to go. Now, when we're focusing just on these coefficients, just on these numbers from Pascal's triangle, notice that the second number in the row will tell you what row you're on, and it's also equal to n. So instead of me having to sit here and go, okay, this is the 0 row, the first row, the second row, the third row, the fourth row, the fifth row, instead of having to count down to that fifth row, I can always see that the second number in the row automatically tells me what row I'm on, and it tells me that that's what my n value is, like x plus y to the n. That would be the row that goes with x plus y to the fifth. Now, they give me there on page 656 4 observations about binomial expansion. So these just came straight out of your book there on page 656. The first one says, in each expansion, there are n plus 1 terms. Okay, look at, if you would, the fourth row down here. In this fourth row, I've got 1, 2, 3, 4, 5 terms. And it was the fourth row, so n is 4, so that would be 4 plus 1. That'd be 5. The second thing it says is in each expansion, x and y have symmetric roles. The powers of x decrease by 1, the powers of y increase by 1. So again, look at that fourth row. This was the fourth row, so we started with x to the fourth, and then we're going to decrease by 1. X to the fourth, x to the third, x to the second, x to the first, no x. The powers of y are going to increase by 1. So we start off with no y, or y to the 0, and then y to the 1, y to the 2, y to the 3, y to the 4. The third thing they tell me there is that the sum of the powers of each term is going to be n. For instance, in this expansion on the fourth row that we've been looking at, the sum of the powers of each term is 4. Like if I go through here and I add up my exponents, I have 4 and nothing, so that's 4. On this term, I have x to the third and y to the first, so 3 plus 1 is 4. On this term, I have x to the second and y to the second, 2 plus 2 is 4. On this term, x to the first, y to the third, 1 plus 3 is 4. On this one, y to the fourth, and no x, or x to the 0, 4 plus 0 is 4. So the sum of the exponents in every term is going to be the same as the row you're on. It's going to be the same as n. Then for number 4, it says the coefficients increase and decrease in a symmetrical pattern. What they're talking about there is, you can see I have a 1 and a 1. I have a 4 and a 4. And then I have that 6 in the center. So it's symmetric. It's balanced on each side. So let's go back to that very first problem that we were saying would really cause us a lot of grief, x plus y to the fifth, that we really didn't want to do x plus y times x plus y times x plus y times x plus y times x plus y. So how does the binomial theorem or Pascal's triangle help me with that? Here's what I can do. Just a few moments ago, we created Pascal's triangle down to the fifth row. So you've already got your 1, 5, 10, 10, 5, 1. Then we're going to go through and let our x's decrease by 1 and our y's increase by 1. So if I'm on the fifth row, then I'm going to start with x to the fifth, and my x's are going to each decrease by 1. So that would give me x to the fourth, x to the third, x to the second, x to the first, and then no x. My y's are going to increase by 1. So I'll start down here with no y, and then I'll have y to the first, y to the second, y to the third, y to the fourth, and y to the fifth. We'll look more at this on the second half of this lesson on another day, but because this is a plus sign right here, then we're going to go through and add each of those. If it were a subtraction sign, we would handle it a little differently. Now, if you had sat here and multiplied out x plus y times itself 5 times, that is exactly what you would have gotten. That's significantly faster and easier. So if you compare that to Pascal's triangle on 656 or to the triangle over on page 658, you'll see that's the exact same thing that we get for x plus y to the 5th. Okay? All right, that still doesn't really help me with x plus y to the 21st, right? Because even though that's a whole lot easier, I don't even want to sit here and draw this thing out to the 21st row, right? I'd be like way down here somewhere. So that's where the binomial theorem can help me. If I have something that's a higher power like that, that would probably be easier to do with the binomial theorem. So on the bottom of page 656, they give me the binomial theorem, and they tell me that in a binomial expansion, there's a fast, easy way to find the coefficients. The coefficients can be found by using Pascal's triangle like we've done already, but they also can be found by using this formula. Ncr is equal to n factorial over n minus r factorial r factorial. If you're looking at that and going, I have seen that somewhere else. When we do permutations and combinations in probability, that's a combination. That's the same formula, exact same notation and everything. So we'll be seeing it again in a couple of days when we're doing our probability. All right, so how does the NCR thing, how does that go with Pascal's triangle? Well, n, remember, is the row that you're on or the exponent that you're expanding your binomial to, right? So let's come back here to this 4th row that we've been talking about. That's x plus y to the 4th, so that means that n is 4. So you'll notice for every one of these coefficients, every one of them has a 4 in the place of n. R is the second number that I'm going to need to know. R is going to be the location that it is in that row. We're going to start counting with 0. So just like we count the rows down by 0, we're going to count the terms across our row starting with 0. So it's going to go 0, 1, 2, 3, 4. So 2 different ways that I could get those coefficients. If I did 4C2 using that formula, I would get 6. Or I could build the triangle down and get 6. So if they gave me something like x plus y to the 21st, they're not going to have me write the whole row. They're usually just going to ask me for one particular term. Like in this case, what is the 3rd term in x plus y to the 21st? So here's what I could do. I could say, okay, if it's x plus y to the 21st, I automatically know that n is 21. So I can come over here and say, okay, the 3rd term is going to be 21c something. Then remember, we count across our terms starting with 0. So this would be 21c0, 21c1, 21c2. I also could get my x's and y's, because remember, my x's count down, so I'm going to start with x to the n, so that would be x to the 21, x to the 20, x to the 19. And my y's count up, so that would be no y, y to the 1st, y to the 2nd. So that would be the 3rd term of x plus y to the 21st without actually having to count out all 21 rows or multiply it out 21 times. They're going to want me to give a number for 21C2. They're not going to want me to leave it that way. So how do I get a number for 21C2? Well, I'm going to use that formula, that NCR formula. All right? So if they wanted me to find, let's use a smaller one for an example. If they wanted me to find 8C2, what would N be? 8. What would R be? 2. So let's plug that into that formula. That formula says take n factorial over n minus r factorial, r factorial. Back on section 9.1, we did that exact same problem right there. We did 8 factorial over 6 factorial, 2 factorial. We did 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 over 2 factorial, 2 times 1 times 6 factorial, 6, 5, 4, 3, 2, 1. At that point, we said you could also abbreviate that. Instead of writing 6, 5, 4, 3, 2, 1, you could just leave it as 6 factorial in the top and the bottom, because either way, that 6, 5, 4, 3, 2, 1 or 6 factorial, whichever way you wrote it, would cancel out. And so that would leave you with just 8 times 7 in the top, 56, and 2 in the bottom. So when you divided, you would get 28. Exact same example that we did back on 9.1. We already know how to do that type of problem. What they were setting us up to be able to do was our NCR to get our coefficient. Here's another one of those. Not only will they write those coefficients like we saw right here, 8C2, sometimes to abbreviate them a little bit, they'll write it this way. They'll write the N on the top, the R on the bottom, and they'll put it in parentheses. When they do that, I could rewrite it in this way if it makes me feel better. So these two are equivalent. Whether they write it this way or whether they write it this way, it means the same thing. I use the exact same formula. So we've already done these before by hand, and we've just reviewed another one by hand. You also can do these on your calculator. Grab your graphing calculator if you would. You have an NCR button on your calculator. But before you type anything in, let me mention something to you. You're going to have to tell it the N value and then hit your NCR button and then tell it your R value. Okay? So let's go back and do that 8C2 that we were doing just a second ago. We did it by hand and we got 28. All right? If I were going to do this on my calculator, I would type in 8 and then I would go to Math and use my right arrow key to go over to probability, and then scroll down to number 3, NCR. And then I would put in my R value of 2. Hit enter and it'll give you that 28. All right, try the second one. Try 10C3. So you're going to put in 10, math, arrow over to probability, go down to number 3 or hit the number 3, either one. It'll put NCR on there and then tell it what your R value is and hit enter. Are you getting the 120? Okay. All right. So the last thing that they ask us to do here is they say if we give you a row of Pascal's triangle, we want you to give us the next row. So they've given us the 7th row of Pascal's triangle and they say, tell me what the 8th row would be. So what's it going to start with? 1. Always starts with 1. So then what are we going to have? Then what? Keep going. $35 and $35?
70.
And then it's symmetric, right? So that makes it nice because I end up doing the exact same sums that I did just a second ago. And that would be the 8th row of Pascal's triangle. Now, here's the cool thing that we want to catch. Up here, we did 8C2 by this formula. Down here, we did 8C2 by Pascal's triangle. We got 28 both times. 2 different ways that we can find the coefficients. Something else that'll be a shortcut for you is any time your R value is 0 or your N and R values are the same, that answer is always going to be 1 because that would be the first entry or the last entry. And remember that idea of symmetry giving you the same answer, because sometimes that will help us find our answers quicker as well. If we've already found one of them and we recognize the other one's symmetric, then that would give us the other one as well. All right, so here is our homework for tonight. As always, we want to be sure we can do these by hand and on the calculator, so I've specified for you here which ones I want you to do which ways.